So right now I have a simple circuit I want to put in as an adjustable nightlight on a breadboard. I have an Arduino plugged into a few LEDs and a light sensor. I also have a potentiometer to adjust the sensitivity of the light sensor and a switch to turn it on or off. This means I have one digital output, the LEDs, which I'm running in parallel to reduce the total voltage drop across them. I have one digital input, which is my switch, and two analog inputs, which are my potentiometer and my photoresistor. That brings me to a total of one digital input, two analog inputs, and one digital output. That means that on my Arduino, if I don't count power and ground, I'm going to be using a total of 4 pins. So I could plug everything in my Arduino Uno, make an enclosure for it, and mount it. But that Arduino Uno takes up a lot of space. To deal with that, I could definitely go down to a smaller size Arduino, like an Arduino Nano. That would work, and it would decrease the amount of space I have to use, but an Arduino Nano can still be a little big for the tiny amount of processing I really need to do with this. So maybe I move down to an Arduino Micro? Well, all of these are possible options. An Arduino Nano will usually cost you somewhere around $15, and a smaller Pro Micro will cost around $20 to $30, depending on the versions you get. That seems like a lot of money for a simple nightlight with only a few inputs and outputs, right? If only I was able to get a smaller, simpler, cheaper Arduino that I could use. Well, you're in luck because we have access to something called the AT-Tiny chipset. This includes several different DIP chips, and DIP just stands for Dual Inline Package, meaning it's a chip that has 2 rows of pins that are physically parallel to each other. You may recognize that other chips, like the H-bridge you're using, also incorporates the DIP configuration. You may also have an Arduino that has a chip called an ATmega328P, which is a DIP IC, or Dual Inline Package Integrated Circuit. Others may have the same chip, called an ATmega328P, in a TQFP, or Thin Quad Flat Package, meaning it's a thin square chip with 4 sides of pins. These chips are functionally the same, but they mount differently. Anyway, we won't get into the semantics of chip packages any further, but I do want to get back to this AT-Tiny chipset. This is basically a scaled-down Arduino, and it comes in a family of different chips, the most common of which is the AT-Tiny 85. You can think of this like a tiny Arduino, hence the name AT-Tiny. This little chip has a total of 5 pins, 2 of which can be used as PWM pins, and the other 3 can be used as analog input pins. All of the pins can be used as digital output or input pins. Along with that, we have a 5-volt pin, a ground pin, and a reset pin. One of the best parts about this chip is that it costs around $2.50 on SparkFun, or you can get them for as little as $1.20 each from wholesale suppliers like DigiKey, or even less depending on the quantity you purchase. If you need something like 100 little microcontrollers all spread out for some kind of simple experience, and you don't want to spend literally $1,500 on Arduino Nanos, you can just go to DigiKey, buy 100 of these AT-Tiny 85 chips for $1 a piece, and save yourself $1,400. I'll go ahead and put this circuit together, and with this optional USB programmer, which just makes it easier to load code onto the chip, I'll upload a simple sketch that adjusts my light depending on how light or dark it is, and that just turns off at some point when the room gets bright enough. I can adjust the sensitivity of all of this using the potentiometer, or I can tell the light to turn off using the switch. If you didn't want to shell out the $15 for this programmer, and you already have an Arduino handy, you can also just follow a guide that walks you through programming the chip using a breadboard and some jumper wires directly from an Arduino. Now, maybe you still need a few more inputs and outputs, but you still need a really small project space. In that case, you might want to move up to the AT-Tiny 84, which has 12 GPIO pins, and GPIO just stands for General Purpose Input Output. Don't ask me why it's called the AT-Tiny 84 and it has more pins while the AT-Tiny 85 has fewer pins. I don't know. In fact, the whole family of AT-Tiny chips has a ton of different ICs that might be useful depending on the number of pins you need, the amount of memory, the number of analog versus PWM pins, the communication protocols it can handle, the package type, and much more. For everything we're doing here, the AT-Tiny 85 and the AT-Tiny 84 will likely be fine for the projects you're doing. But let's say you actually need all of the pins from your Arduino Uno. Maybe running a whole array of lights or a ton of buttons, and you really do need all 20 I/O pins provided with the Arduino Uno, or equivalent board like the SparkFun breadboard. But you don't want to use up all the space the Arduino body takes up, or maybe you just don't want to pay for a $25 Arduino. You can follow a guide provided by the Arduino website, get a few components, put everything together, and have a perfectly functional Arduino on a breadboard, or solder it onto a breakout board. In fact, for all of the parts you would need, even assuming you don't have access to LEDs, buttons, or resistors, you can buy everything you would need to make a functional Arduino Uno on a breadboard for a grand total of around $5.65. The whole point is it's very possible that your project might not need a whole Arduino, or even a smaller version of an Arduino, but rather just a chip. Keep in mind, however, these chips come with some drawbacks. Arduinos tend to have circuitry that makes them fairly foolproof, so if you end up shorting an actual Arduino Uno from 5 volts directly to ground, it will just shut itself off. With these DIY versions, you will not have all the safety and utility of an actual Arduino, and you will have to program them using special boards or an external Arduino. To be fair, you could make the same mistake 4 times on this version of an Arduino and burn out all 4 of them. As long as the 5th one worked, you would still be just about the same in terms of cost is if you had made the mistake and burnt out a single Arduino Uno. Now, if you wanted to make your own tiny version of Arduino, and you didn't want to use a breadboard, and didn't want to use an ugly-looking prototyping board, you could get into PCB design, which, as I've said before, isn't nearly as complex as you might think it is, and can really make a project shine when it comes to look and functionality. PCBs are surprisingly affordable to make as well. If you have any desire to make a PCB, you could make your projects even smaller than you might normally be able to with an ATtiny DIP IC. If that's something you're interested in, definitely send me an email about it, and I can show you how to make a simple PCB that will accomplish what you need, and will likely be less expensive overall than an Arduino itself. Now I'd like to switch gears and talk about a few different kinds of wireless communication. Unfortunately, I don't have a ton of wireless communication devices with me, so a few of these will just be explanations about what you could do if you had these devices. We will, however, go over the pros and cons of each of these wireless devices. I'm going to cover Bluetooth, Wi-Fi, radio frequency, infrared, GSM, and GPS, and then one that isn't technically wireless communication, but rather just wireless technology, and that's wireless charging. First, let's talk about wireless technology as a whole. What is it? How does it work? How does the information actually travel through the air? How is Bluetooth different from radio frequency or Wi-Fi? Well, let's start by talking about light. You may wonder, what does light have to do with anything? Well, it turns out, Bluetooth and Wi-Fi and RF are all just light waves. To be fair, they're way lower on the electromagnetic spectrum than humans can see. Before we get into that, let me ask, which of these do you think has the shortest wavelength, aka the most energy out of all of these things that we're going to talk about, assuming identical wave amplitudes? The answer is D, the color blue. Some of you might have thought, well, my microwave literally heats food because it has so much energy, so it has to be pretty high power. As it turns out, your microwave works on similar frequencies as your Wi-Fi, 2.4 GHz for your microwave and 2.4 GHz for your Wi-Fi bands. The color blue has a much shorter wavelength. That being said, if you ever turn on your microwave and your Wi-Fi gets really spotty all of a sudden, get a new microwave. Because all the shielding on it is leaking that electromagnetic radiation, which is then interfering with your Wi-Fi signal. To be honest, it isn't actually that dangerous if you do start getting signal interference, because microwaves do absorb the vast majority of those electromagnetic waves. So I take that back. Don't throw out your microwave, just make sure your router is far away from your microwave. Or alternatively, just switch your Wi-Fi router to a 5 GHz band instead of the 2.4 GHz band. So what's the difference there? Why can't you heat up food by sitting it near the antenna of your Wi-Fi router? Well, there are two reasons. Amplitude and concentration. Your Wi-Fi antenna is meant to spread the electromagnetic radiation as far as possible instead of concentrating it on a specific spot. By the way, all of these communication methods are in a band of what's considered non-ionizing radiation, so you're not going to grow extra limbs or get tumors because of Wi-Fi or Bluetooth signals. In terms of concentration, your microwave is made to concentrate all that radiation into your bowl of beans, or whatever you have in there. It has a ton of shielding that's either meant to bounce or absorb that radiation, so that only whatever is inside of the microwave is absorbing all of that energy. The other half of the story is the amplitude of the electromagnetic wave, which carries much more energy. Your Wi-Fi, while it works on the 2.4 GHz range in terms of frequency, it only operates at a maximum strength around 200 milliwatts, or 1/5 of a watt of power. Your microwave, on the other hand, pumps somewhere between 800 and 1,200 watts of power, meaning that your Wi-Fi router uses 0.0167% as much energy as your microwave. That means your microwave puts out well over 6,000 times the amount of power as your Wi-Fi router every second. Imagine the difference in your electricity bill if instead of running your Wi-Fi router for a whole month, you ran your microwave at full power for a month. This all brings us back to the question, what does light have to do with this? What really are electromagnetic waves? Well, without getting too complicated, you can think of electromagnetic waves as different wavelengths of light. That is a really simple explanation, but for the sake of this class, that's all we really need to know. We know light doesn't need some kind of medium to transfer through, but in fact transfers through vacuums the easiest. The more stuff, like walls and doors and concrete and air, that it has to go through, the worse the signal gets. For many electromagnetic waves, the smaller the wave, the more energy it has, but also the more stuff it bumps into, meaning it can travel shorter distance before losing strength. This, along with how waves spread out and get weaker as they travel, is why your Wi-Fi router supports 2.4 GHz and 5 GHz bands. Your 2.4 GHz band will work from a longer distance, but your 5 GHz signal will send more information. If you're close enough to have a good signal strength with your 5 GHz band, the increase in frequency allows faster data transfer between the router and your device, but it also limits the distance. The 2.4 GHz band operates at a lower frequency, meaning it can't send as much information as quickly, but it also doesn't bump into as much stuff, and doesn't spread out as much on the way to your device, so it can travel further. While this example is oversimplified, it's a good basic concept to understand and remember the differences between higher and lower frequencies and how they transmit data. So Wi-Fi, Bluetooth, FM, and AM radio, and even infrared and visible light are all the same thing, electromagnetic waves. They just happen to be different frequencies. Bluetooth and Wi-Fi, however, often operate right around the same frequency of 2.4 GHz. The difference here is the usage case for each one. Wi-Fi uses a set of protocols or rules when passing data back and forth. Bluetooth uses a different set of protocols. Bluetooth and Wi-Fi also use different amounts of power, changing the amplitude or height of those waves again, meaning Wi-Fi uses more energy, but can also go further than Bluetooth. If you don't believe me, try putting your phone next to your router. Listen to some music on Bluetooth headphones and move away from your phone. Keep going until you start getting distortion in the music, because Bluetooth is fading out. Try that again, but this time stream the same music from your phone and move it away from the router. See how much further you can move before you start getting distortions in the signal? You should be able to move further with Wi-Fi on your phone than Bluetooth on your speaker or earbuds. That all has to do with how much energy is being broadcast out of a Wi-Fi signal versus a Bluetooth signal. I want to take a poll here. Knowing this information, if I tell you that AM radio operates at 500 kHz to 1.5 MHz, and FM radio operates between 88 and 108 MHz, which one can travel further? Remember the example about 2.4 versus 5 GHz Wi-Fi, and which one can send more information versus which one can travel further. Assume that both AM and FM radio stations are broadcasting at the same power initially, meaning that they're sending the same amount of power through their antennas to broadcast their various frequencies. The answer is AM radio. AM radio operates at a lower frequency, meaning it carries less energy, but it can also generally travel further. When it comes to Wi-Fi and Bluetooth chips that you can see and use for projects, there are tons of options. For Wi-Fi, you can get a whole board, something like an Adafruit Feather, or a generic board like an ESP8266 or an ESP32, all of which have Wi-Fi antennas pre-installed on the board. You can also get other manufacturer brands like SparkFun's ESP32 Thing, the SparkFun Photon Red board, the Particle Photon, or even the Arduino Uno Wi-Fi R2. Each of these has integrated antennas, so you don't need to worry about buying the proper antenna. You can just plug these in, make sure you have the right board selected from your Arduino board library. Some of these board configurations may need to be downloaded before the Arduino IDE will recognize the board. And then you put your program on the board and use it in wireless projects. Now for Bluetooth, there are a lot of options as well. You could get the Arduino Nano BLE, the PyCom FiPi, the XB3 with both Wi-Fi and BLE connectivity, or the SparkFun Pro NRF 52840 Mini. The SparkFun ESP32 Thing also has Bluetooth as well as Wi-Fi capabilities. Fun fact, Bluetooth actually comes from a 10th century Viking, King Harald Bluetooth Gormson, who united Denmark and Norway through improved communications. He was called Bluetooth because of a rotten tooth that looked bluish-gray. The name was originally a joke among the creators of Bluetooth protocol, but after a deal to rename it Radio Wire fell through, and the name spread quickly, the Bluetooth communication method was born. Our current symbol for Bluetooth is actually a combination of King Harald Bluetooth Gormson's initials. I think at this point we can move on to a different kind of wireless communication. Let's talk about radio frequencies. We talked a tiny bit about AM versus FM radios. The problem with those radio signals is that they're too strong for us to use. If we found a way to broadcast at the same frequency and amplitude as some of these stations, we would be able to start pirate radio stations, and we would shortly have rude men in suits knocking at our door saying something about being from the FCC and not transmitting AM or FM bands more than 200 feet, and $10,000 or 18 months in prison and a class 4 felony and stuff like that. Radio frequencies range from 3 Hz all the way up to 3,000 GHz, meaning they range in pulses from 3 times a second to 3 trillion pulses per second. Some radio frequencies can transmit between 3 and 30 Hz, which is considered to be the ELF or extreme low frequency band of radio. These signals have physical wavelengths between 100,000 and 10,000 kilometers respectively. In freedom units, that means 62,000 miles when the signal is near the 3 Hz range, or 6,200 miles near the 30 Hz range. On the high end in our terahertz range, meaning literally trillions of pulses a second, our wavelengths are around 0.1 millimeters. The freedom units on that are around 3.9 thousandths of an inch. Much more common frequencies are between 300 kHz and 300 MHz, which include things like AM and FM radio, RFID, and television broadcasts.